So yesterday we looked at the photoelectric effect experiment, and this is one of the most famous experiments in modern physics. And the cool thing about this very most famous experiment is Albert Einstein actually won the Nobel Prize for explaining how this works and why it works. All we did was we just took some frequencies of light, different frequencies, we put that light on a metal, which then knocked out electrons. We call those photoelectrons because they pick up that photon energy. And we just use a voltmeter to try to figure out how much voltage is needed to stop those electrons. The experiment, when we looked at it in the example yesterday, just in that little lab, we saw that the electrons came off of this piece of metal when they got energized by the light. So the light comes in, energizes the electrons, they move across a vacuum surface, they carry then that electricity through, and it goes all the way through the circuit. If you use a voltage, okay, so here we're using a battery and we can increase and decrease the amount of voltage, we can get it so that the amperage is zero. When the amperage is zero, you'll see the electrons kind of just sit out here and float. They really don't move at all. So instead of completing the circuit, a few do, but not enough to really give us any current. From that, we can figure out the voltage, and we said that the voltage was equal to the EV. And then we can take the EV and convert that into joules, and we can plot the frequency versus, or I'm sorry, plot the energy in joules versus the frequency. We get a straight line, and then you remember the rest of the experiment. The slope of the line is Planck's constant. We know where it crosses the y-axis. That gives us the wave function, or gives us the work function here. That's the experiment in a nutshell, and that's kind of what we did yesterday. So if we go on in this, we found out that there were some strange results. The voltage necessary to stop the electrons didn't depend on the intensity. It only depends on the light's frequency or the color. So the photoelectrons are not released below a certain frequency, regardless of the intensity of light. So we call that the threshold frequency. The release of those photoelectrons happens immediately. And even if you don't have much light, so they say that that's feeble light, as long as you have that frequency and it's above the cutoff frequency, we know that you're going to get electrons coming off. You do this for different frequencies, okay, or different intensities, I guess. We did notice that there was a little bit of a change when we did intensities. So here are three different intensities of light, I2, I3, and I1, and we notice that those intensities increase. That does not affect the stopping potential. Okay, that does not affect the stopping potential, but it does increase the number of electrons. Nonetheless, the stopping potential is always the same. The only thing that the current really changes is the intensity. So we know that current is also I. If you remember the equation, V is equal to IR. So it's really easy to remember that the intensity and the current, so this is current, can be the same thing if you want to think about their relative values. The next slide talks a little bit about how the frequencies are a little bit different. You'll notice that the frequencies here have different stopping potentials. However, we also notice that the intensity at the same intensity for the frequencies really doesn't change much. So here is our stopping potential. Here is the stopping potential for each one, and then you'll notice that as you have higher energy, you have a bigger stopping potential. Remember, blue is pretty high energy, green is in between, and then red is a really low energy photon. For the next one, the kinetic energy of a photoelectron can be determined from the voltage. So if it takes 6.5 volts to stop an electron, we then know that it has 6.5 eV of kinetic energy. And remember that these are typically negative because we're talking about slowing down the electron. So we're using energy to slow it down. That's why we have the negative. Doesn't really mean that it's got a negative value. It just means that that's the direction we're trying to impart onto the electron. This is a graph of what we've been talking about over the past couple of days. So this is the experimental graph. Remember, y is equal to mx plus b. That's just for the equation for a line. So it's the linear equation. If you go through and we actually plot the kinetic energy in joules versus this line is going to have to end up being frequency, so you'll see that right here. If you plot those two things and you find the slope, that should come out to be Planck's constant. If it does, and it's really close, if you extend the line back and check and see where your y-intercept is, that is the binding energy. So if you're doing this experimentally and you had all these dots, you could then go through and solve for H. If H looks like it's right, if it's not, you can move it one way or the other depending on whether your value is too high or too low. And then that helps you end up finding out what that phi value is. And remember, this is minus because you're finding down on the bottom. When we did the lab in fourth period, we actually used negative values, so you get a little bit different graph. Actually, we probably want to use positive values like we did here so that our slope ends up giving us a line that goes back and the y-intercept is down below. For the next section, what we're going to do is we're going to talk about the difference between the energy of a photon and the energy of something that actually has mass. Photons, or little light particles, they do not have what we call rest mass. They have to travel at the speed of light, and nothing can travel at the speed of light unless its mass is absolutely zero. Now, we do say that photons have a fixed amount of energy. We know that from E is equal to HF. If you remember, photons of light that are violet, okay, they have a very high energy. So their energy is pretty big. And red, on the other hand, that energy is pretty small in relation. Ultraviolet is much higher, and then gamma photons are actually the highest energy that you can get. We can calculate how much mass we would have to destroy, that would have to be destroyed to create a photon by using Einstein's famous equation that he did not win the Nobel Prize for, E is equal to mc squared. The first problem we're going to do says calculate the mass that must be destroyed to create a photon of 340 nanometer light. So we want to find out the mass that needs to be destroyed in order to generate that light. So let's go ahead and just go through this one. Essentially what you can do is say the energy and the mass needs to be equal to the energy of the photon. We know that E for mass is equal to mc squared, and the energy of a photon is h times f, which we also know is hc over lambda. If we go through and combine these equations, we can divide both of these. Okay, so we're actually going to get rid of this hf. Let's just go ahead and cross it off. If we divide both sides by c squared, so we're going to divide both these by c squared, you end up with m is equal to hc divided by c squared lambda. And because this c crosses off and one of the c's here cross off, now we've got m, or the mass, is equal to h over c times lambda. So mass would be equal to h over c times the wavelength of light. At this point, we plug everything in, 6.625 or 6.63 times 10 to the negative 34th. We're going to divide that by the speed of light times the number of meters. Remember, we don't want nanometers. We need to use meters because of the constant and because of the speed of light is in meters per second. And when you're done, you'll find out that it doesn't take very much mass in order to create that amount of light. But remember, you're destroying that mass, and when you destroy that mass, it does release enough energy that it produces a photon of light with a 340 nanometer wavelength. The next problem, we're going to start talking about momentum a little bit. Photons don't have a rest mass, yet we know that they have momentum. Remember, we talked about you can have UV radiation that burns your skin, so that's a type of photon. Changes some things in your skin. If you look into a laser, if you look at a laser beam, you can burn your retina pretty badly too. The momentum is given given a large number of photons, they actually create a pressure. So a photon's momentum is calculated using the following equation. So we can say momentum is equal to the energy of a photon divided by the speed of light. That's equal to hf over c. And we could also say that's just h over lambda, because we remember that F is equal to c over lambda, so the c's cross off, and then we're left with this. So you're going to see all three of these, they're all equal to momentum. So we're looking at the momentum of a photon itself. For the next slide, we have experimental proof that the momentum of photons does exist. This experiment is called Compton Scattering. It's not named after Mr. Compton. That's not why he left. He didn't discover it. He's selling houses now, so he's making more money than we ever will. It's proof that photons have momentum from this experiment. They actually took high-energy photons, they collided those with electrons, and we saw that it exhibits the conservation of momentum. We work Compton problems just like other conservation of momentum problems, and we've done those in honors physics, except for the momentum of a photon uses a totally different equation, and we're going to look at some problems that'll do that for us. The first one says, what is the momentum of a photon that has a wavelength of 620 nanometers? If we do this problem, we're going to use the equation P is equal to h over lambda because we don't have frequency, instead we have wavelength. We're going to go ahead and just plug everything in. So we've got 6.63 times 10 to the -34th. We're going to divide that by that 620 nanometers. The meters on top, the meter squared on top here, this becomes meters because the meters on the bottom crosses off. The seconds squared on the bottom right here becomes seconds because this goes away, and the final unit is a kilogram times a meter per second, which we know is momentum. So the momentum of a photon that has a 620 nanometer wavelength is about 1.07 times 10 to the -27th, which is very small because a photon is very small, but if you get a lot of them, you end up with a lot more momentum. Next thing they have us do here is what is the frequency of a photon that has the same momentum as an electron with a speed of 1200 meters per second. So what is that frequency? In order to do this problem, we need to say that the momentum of an electron is equal to the momentum of, and this is a photon, not a proton. Be very careful. We know the mass of any particle is just mv, so the momentum of any particle is equal to mass times velocity. And the momentum of a photon is equal to h over lambda. So for this one, we're going to go through, we have to try to find frequency. So instead of this, we're going to use c over f. And when you rearrange this, you end up with hf over c. That's equal to the momentum of a particle, which is me times ve, because that's an electron. If you just combine the two equations, rearrange for f, you end up with the frequency is equal to the mass of the electron times the speed of the electron times the speed of light, all divided by Planck's constant. So all that math is done here, and you end up with a frequency of 4.95 times 10 to the 14th. Remember, a hertz, that's just 1 over a second, or a second to the -1. For the next one we have here, we're going to talk about wave-particle duality. We know that waves act like particles sometimes, and particles act like waves sometimes. This is really easily seen for very energetic photons, so gammas or X-rays, or very tiny particles like electrons or nucleons. So that shouldn't say elections, that should say electrons or nucleons. Nucleons are protons or neutrons. If you have a Geiger counter, we can actually measure those energetic photons, the gamma rays, because you can hear that Geiger counter click. And it clicks because they have a lot of energy and they hit the little device, and when they hit it, that energy is transferred and transformed into audible sound. And then we can count those clicks. So this next one says particles and photons both have energy. We know that the kinetic energy of a moving particle is 1/2 mv squared. A particle has most of its energy locked up in its mass. So if you split an atom, you know you get a lot of energy. That's where we get our nuclear bombs. And a photon's energy actually calculated using its frequency. So we can set those two equal to each other, and that will really help us kind of look at some different problems here. For a particle that's moving, we know that momentum is equal to mass times velocity. For a photon, that's just h over lambda, so Planck's constant divided by the wavelength. And we did go through and figure out that if we look at the units for this, it does